laying some groundwork for both sort of the conceptual and theoretical groundwork for what we're going to talk about this afternoon. So the main goal of this is to introduce probabilistic modeling. So there's only 3 hours of lecture today, so it's kind of a compressed whirlwind tour of probabilistic modeling. So we haven't been through before. Hopefully it gives you at least a bit of a flavor of the kinds of things that are being used. And then the lab in the morning will actually give you a chance to use some of these tools in combination with more sophisticated machine learning techniques to do some solve some practical tasks. The task in the lab in the morning is activity recognition video. So, like I said, it's going to be a bit of a whirlwind and quite compressed. So feel free to interrupt at any point if you have any questions. I'm going to try to load this. Some of it is a bit technical, and as we go through, it might just be difficult to absorb it in such a short amount of time. But I'll try my best. So, like I said, we're going to talk about probabilistic modeling. So, due to the Bayesian networks and the strategies for fitting Bayesian networks to data, sort of the primary strategy we're talking about today is maximum estimation and a slight generalization of map estimation. The idea, like I said, is to be able to apply these things for fitting probabilistic models to simple data sets, and we'll really build on this in the second half of today in order to develop really interesting algorithms for topic modeling. So where we're starting today is what we call machine learning a supervised learning problem. So someone gives you a collection of data observations. So I'll try to denote data observations here as x's and y's. In a supervised learning problem, you're given a collection of x's and a corresponding set of y's, and we assume that the y's are some kind of label that you would like to predict. The goal of supervised learning then is to fit some model to the data set so that given some new x, you can predict hopefully quite accurately its y. So there's lots of different ways to do this. If you spend any time working with machine learning algorithms, there's hundreds and thousands of them for a variety of different applications. But the standard approach to these problems is all the same. Someone gives you a bunch of data. You use that data to build a model under some notion of model fit. And then you can evaluate that model basically by looking at how well it solves your supervised learning task. All right. So to be a bit more concrete, so a really simple example of a supervised learning problem is a spam email detection or classification task. So here, you're given a collection of emails, each of which comes with a label, spam or not spam. And our goal, for example, might be to build a spam classifier. So given some new email, we'd like to say, is it spam or not spam? So that's the prediction task. There's sort of separate tasks we might consider too, and what we'll be focused on mostly today is a model learning task. So here we'd like to model the probability distribution of spam emails. The idea being that what we're really thinking of in a lot of these machine learning applications is not only does there exist a bunch of data that comes with correct labels, but that data is generated from some random process in the world. This is a very Bayesian statistical approach to life in the universe, but it actually is the one that underlies most of the standard machine learning algorithms. We assume that there's some generating distribution for the data. So the model learning task then is to figure out what is that generating distribution. And in fact, if we fit such a distribution here, we could generate spam emails, whatever that would really mean. Again, we call problems like this spam email detection supervised learning because for every different one of the data points, we're told whether or not it's spam. Right? It's not a separate problem. Right? We're not just given a bunch of emails and then ask, are they spam or not spam? Right? That's sort of a different problem. We don't know what the right answers are in that scenario. Whereas here, we assume that some poor soul spent a lot of time going through emails and saying spam, not spam. Right? So there's some human intervention in the loop here. Right. So in order to put this into the supervised learning framework I specified before, what we'll have to do is take our sort of raw data, in this case the emails, and we need to turn them into what we call feature vectors. So we'll need to make them some kind of mathematical object so we can talk about mappings from x's to y's. So there's lots of different ways one could do that. So for example, in the spam email classification task, we might take each email and basically turn it into a big vector of, in this case, let's say, for example, indicator variables. So let's suppose we create a big vector whose ith component just tells you whether or not the ith word, say, in the dictionary is in this email. Right? So just a 0, 1 kind of thing. So you give me an email. I look, I have this, big vector. There's 10,000 words in the English language. So I just, enumerate them all starting at, A through Z. And, when I look at the one particular entry of this vector, it's either 0 or 1, indicating whether or not that, that word actually occurs in the specific email. In addition, right, I can have another indicator variable, right, that just tells me whether or not the email is spam or not spam. So I can take every email and I can process it then into a vector, x and y, where x is this big long vector of all the entries in the dictionary, and y just tells me whether or not this particular email was spam or not spam. So this is a standard preprocessing step. I think in some of the previous days you focused on sort of feature extraction and different ways you can represent data. It's not unique, right? You notice that there could be multiple emails that map to the same vector here. We would hope that all the emails that map to the same vector will all be either spam or not spam, so that we can actually apply the techniques. We can generalize this too. We don't have to have just features corresponding to whether or not a word occurs. Right? For example, we could count the number of capital letters or the amount of punctuation in an email. Right? These things would be other things we could augment this feature vector with. So the idea is that once we've sort of converted our emails into this vector form, we can then apply whatever standard machine learning techniques that we would like in order to basically solve this prediction task. Right? Given some new email, we construct its sort of feature representation x, and then our goal is to predict the correct y. Right? Ideally with very high accuracy in practice. The idea that we'll take in this lecture and in the afternoon as well, as I said before, is one of probabilistic modeling. So we're going to assume that the emails are generated by some random process. So we'll really think of our feature vectors not just as corresponding to some vectors in some n-dimensional space, but actually representing random variables. Right? So I really think of the ith entry of that feature vector as being a random variable corresponding to whether or not the ith word occurs in any email. Right? So now we're thinking distributions over emails. Our goal then is to learn a model that represents basically the relationship between the features and the correct label. Right? We fit this model to data, and once we fit this model, right, our goal will be to use that model to predict the correct answer. So you're a very quiet group, so feel free to jump in if you have any questions. I tried to keep it. I tried to keep the motivating examples relatively straightforward. So we'll see for this task a really simple probabilistic model can actually solve this problem with very, very high accuracy. In fact, something like, depending on how you choose your features, you can get over 98% accuracy with very, very simple models for this problem. So it's in some ways, it's not a very complicated or difficult machine learning task. But the ideas that we'll develop here really apply more generally, well beyond spam email classification. Sure.
So you said choosing features, but then you said the features are random variables?
So we get to pick the features. So in a lot of these machine learning problems, right, the first step really is to pick some kind of representation for the problem you're trying to solve. So the representation here is the featurized version of your data.
Sure, but what does random mean in this context?
Right. So like I said, we're really going to think of our data as being generated by some random process. Right. So someone gives you an email. I think of that email as being generated like independently. Emails are being sampled somehow from the universe, right, independently at random from some probability distribution I don't know.
Right. Random variable from like the statistical point.
Yeah, that's right. So I'm thinking of it as a random process. You might not think of email generation as a random process.
For solid reasons, but sure.
Yeah, for solid reasons. However, it turns out that if you have enough data, this is actually a really reasonable thing to do. In fact, even if you're more familiar with some of the other machine learning techniques, they basically make the same assumptions. So everything is assuming that there's some underlying probability distribution that generates the data, right? And we're trying to model that thing in some way.
Yeah.
Yeah. Whether or not you love thinking about the world as a Bayesian statistician or not, right? This is really the approach that we're going to take here. Hopefully, by the end, I can convince you that it's not an unreasonable way to think about solving these kinds of problems.
I'd be happy if it works. That's fine.
Okay. Well, that's practical. Okay. So the type of models that we're going to fit, so there's lots of different types of ways we can think about fitting probability distributions to data. The one that we'll focus on here, simply because it's the easiest, are Bayesian networks. So you shouldn't confuse easy with generality. They actually apply quite generally. It's just that they happen to be a little bit easier to understand. There's more complex models that are in some ways equivalent and simplify representation a bit, but they're harder to, the theory is a little bit tougher to work with. So a Bayesian network is basically a probability model, and it's described by two things. The first thing is a directed acyclic graph. So I've got a graph right here. It's directed in the sense that it consists of a collection of nodes and directed edges. So there's a directed edge from x1 to x3 in this graph. And we say it's acyclic if there's no cycles in the graph that you obtain by following the directions of the arrows. Right? So what that would mean is there's basically no way to go from x1 back to x1, right, proceeding in the direction of the arrows in the graph. That's a bit technical. So the reason it's important is that in these models, basically these edges denote correlation, and it's a specific type of directed correlation. I'll explain that a little bit more in a second. If you have a cycle in the graph, it introduces a weird dependency that can't be resolved in the way that the theory is put together. Again, though, that doesn't reduce the generality of the approach. Basically, anything can be put in this form, though it might be more or less natural depending on the application. So, like I said, these models have two pieces. They have a graph, and then this graph, together with this graph, you also have to specify the actual model of the probability distribution you're fitting, and that the form of that probability distribution is basically determined by this graph. So how should we think of Bayesian networks? Well, in this graph, each one of the nodes in the graph is going to correspond to a random variable, or feature or label. So in our context, right, in our email problem, right, we can think of these x's as corresponding to either the label or whether or not word 5 appears in an email. The edges, like I said, correspond to sort of a direct statistical correlation. So if you have an edge from x3 to x5, it really means that there's some statistical dependence between x3 and x5. If you don't have a direct edge between a pair of variables, they could still be correlated through paths in this network. But a direct edge means a direct statistical correlation. It's important to point out here, so sometimes when people first see these types of models, it's tempting to think that the direction of the arrows implies some type of causality, like this thing, x1 comes before x3 in some kind of statistical causal ordering. That's not what this means. It just means that they're sort of directly correlated. You can pick the directions of the edges and sort of still have equivalent models.
Right. I was going to ask, because correlation is symmetric, right?
Right. So you can sort of flip the edges. We won't really be able to get into it today, but how easy or hard the model is from a computational perspective really depends on how you pick which directions the edges go. But we're going to ignore that because we only have so much time today. Okay. So once you've specified a graph, the actual probability model that we'll be fitting, we say factorizes over that graph, in that you've got some joint probability distribution, again, over, let's say, your features and your labels. And it can be written as a product of smaller probability distributions. And these smaller distributions are conditional probability distributions of each random variable or feature in your model, conditioned on the value of its parents in the model. So I'll give some illustrative examples in a second. But the point of this is that the graph basically specifies some product of probability distributions that are used to construct the probability distribution that we're going to fit to data. So every different assignment to the parents of a particular random variable, right, introduces a different probability distribution over the values of its child. So let's just see what this looks like. It's sort of best illustrated by example. So this is just the directed acyclic graph I had from before. So in this particular case, the Bayesian network structure assumes that you're given this structure, and you have some probability distribution that can be written as a product of the first variable conditioned on its parents. It doesn't have any, so it's just the probability distribution of x1. The second random variable conditioned on its parents, which is x1. The third random variable conditioned on its parent, which is x1. The fourth random variable conditioned on its parents, x6 and x3. Right? So parents are its immediate predecessors. Right? So the incoming edges, etc. Right? So I just product up these things. That's the probability model that I'm fitting. So in general, not every probability distribution over, say, 6 random variables can be written in this form. The graph structure is limiting us to special types of probability distributions. Right? So this is not all probability distributions. This is a specific subset. Okay? So for simplicity of notation going forward, so I'm going to try to avoid too many of the technical details, but occasionally I'm going to have to write some formulas down, as we sort of motivate how these things are actually used in practice. I'm going to abuse notation a little bit and write the probability that some random variable takes a particular value. It's just the probability of x1. So the probability that the random variable x1 takes the value x1. I'm just going to write this p of x1, where it's to be understood that I mean this. It's just for simplicity of notation. Otherwise, the equations just don't fit on the slide. So any questions about this? So you have some graph. That graph implies that some factorization of a probability distribution. And what we'll be looking at when we think about fitting probability distributions to data is that if we want to fit a Bayesian network like this to data, we'll assume that it can only be a probability distribution of this form. Right? That's the only thing that's allowed. So the graph structure itself implies a lot of different special properties of the underlying distribution. It takes probably 3 or 4 lectures in a course to really get into exactly what the connection is there. Let's ignore that for now and just sort of focus on how structure basically informs the different types of factorizations that we'll be using. All right. So there's lots of other examples of Bayesian network structures and the types of factorizations they imply. So one particularly important one, which will come up in a much more sophisticated form on the lab today, is what we call a directed chain Bayesian network. So here, it's just the random variables are just connected in sequence, one after the other. In such a model, right, the joint probability distribution again factorizes as a product of each variable conditioned on its parent. Every variable has one parent, and they're basically in sequence here. So the assumption in this particular setting is we're fitting a probability distribution of this form when we're trying to fit this model to data. Models like this are good for fitting sequential data, right, where we really do think of x1, x2, x3 as being part of some random process that occurs in sequence. Another model, really common Bayesian network that gets a lot of use is something called the naive Bayes model. It's the one that is typically fit for this spam email classification task. So it looks something like this. You have sort of one random variable that's the parent of every other random variable, and there's no other edges in the graph. It corresponds to a factorization of the joint distribution as the probability of y times the probability of each one of these features, right, conditioned on y. So how will this apply to something like our spam email classification task? Again, remember in that particular supervised learning problem, we think of y, the y random variable is the label, and the x random variables, right, as indicator functions for whether or not the ith word in the dictionary occurs. Right. So if we were trying to fit a naive Bayes model to our spam email classification task, we would construct a model just like this. We'd line up all of all of our feature information, and then add one node for the label, and then just put directed edges from the label node to all of the feature nodes. And then we would fit this model to data. The nice thing about this particular model is that once we're sort of ignoring how we actually fit this model to data for a moment, but once someone gives you this model, right, and a new x, right, we can figure out what's the most probable y value, right, simply by trying all the values of y. And we just plug them in. So just to make sure that we're all on sort of the same page with the way the process works, right, we take our email, we featureize it into this vector x. If it was something we hadn't seen in our training data, right, and so in sort of our data observation set, then we would plug it into this probability distribution, right? So we know the values for x, and we would try both values for y, right? There's only two, 0 and 1. Whichever one was most probable, we would say that's the label that this model is predicting for this email. Yeah?
So this is basically saying conjunction, right?
Yes, sure. Yeah. Though, with some caveats, it's slightly more complicated than that because these are sort of arbitrary probability distributions. It's not it.
If I added an x6, I'd be sort of lowering the chances that this thing actually happens.
Yes, any particular thing happens, but just remember you've lowered the chance that everything happens.
Yeah.
Right. So it's all relative in this framework, right? So that's a good point, right? If I say I had 100 features or 10,000, right? If we really had one for each word in the dictionary, right? Then this thing is a product of 10,000 probabilities, right? This number will be tiny, right? In practice, almost certainly. But it's all relative. We're going to take the log of all this stuff, so it doesn't matter that there's 10,000 of them. There's no sort of numerical, difficulties with doing something.
Oh yeah, that's fine. When I look at it, I see disjunction, and when the math says conjunction, I was like, okay, which one is it?
Questions about sort of the approach, right? So someone gives you a Bayesian network that's specified basically by this structure and a collection of probability distributions, right? The learning task will basically be to figure out how we should pick these probability distributions to sort of best describe the data. Yeah. Okay, so what we're going to spend the rest of the lecture on today is really talking about the precise learning problem that we're interested in solving. So again, to reiterate, our goal is given a collection of data samples, so generically here as think of them, your data observations as just being vectorized features joined with their labels potentially, from some unknown probability distribution. Our goal is to find the Bayesian network that sort of best represents this samples. So I should have, I put it in bold. It's sort of hard to see. Best represents here, should really be in quotation marks. We have to decide what we would mean by, a model representing data and how good or bad it is at representing a particular data set. Once we specify that, right, then we can then basically, it'll boil down to solving some optimization problem to fit, these models to the data. This is sort of the standard process in machine learning. When I teach the machine learning course here at UTD, typically the way I present the materials, basically every machine learning algorithm is this. You pick some model. Oh, nice. You pick some model. You pick some sort of goodness of fit function, right? You then optimize your goodness of fit function over your class of models. The one that comes up highest in your goodness of fit test is the model that you fit the data. This is all basically, most machine learning algorithms basically fall into this framework. It's just a simple matter of which types of models you're fitting and what your criteria is for goodness of fit. So in a typical model fitting problem, right, that we're taking a look at here, there's really sort of two tasks. The first is, if someone doesn't give you the Bayesian network structure, you'd have to learn it. I'm not going to talk about that today. It follows, once you see sort of how the parameter learning works, the same kind of ideas would apply for what we call structure learning, right? Figuring out what's a good representation for the data. The second is parameter learning, which I said is what we're going to focus on. So it's learning the parameters of the model. In the case of Bayesian networks, the parameters are nothing more than these conditional probability distributions. So someone's going to give us assuming that someone gives you the network structure, our goal will simply be to find the choices for the conditional probability distributions that sort of best describe our data. Again, under some notion of best describe. It doesn't go forward. All right. So to motivate how this actually works, I'm going to go to probably the simplest application that I can think of, one that's quite easy to understand. So sort of a classic model fitting problem, which you probably wouldn't really think of as a model fitting problem, is estimating the bias of a biased coin. So let's suppose someone gives us a coin, and it's not perfectly 50-50. So if you flip it, maybe it comes up heads B% of the time, and it comes up tails 1 minus B% of the time. I can think of this as a probability modeling problem. So this one's quite natural because I could actually really think of this as these coin flips as being independent draws from some distribution, right? So it's a little bit more natural than sort of thinking of emails as being generated randomly. Our goal is then to simply just estimate, right, what's the bias of the coin. The reason we can think of this as a probability, a Bayesian network modeling problem is this corresponds to basically a problem where we have one random variable, right, that just tells us whether or not the coin is heads or tails. So this is the simplest Bayesian network you can think of. It has no edges. It's just a single node. The probability distributions here are then the probability of the probability of the outcome. So there's two outcomes, heads and tails, and we just like to fit this to data. Right? So we get a bunch of samples, which here correspond to coin flips. So someone flips a coin capital M times. So NH of those times it'll be heads, and NT of those times it'll be tails, and those are our data observations. Right? And we'd like to use these observations to estimate the bias B. So the procedure we're going to use for this is maximum likelihood estimation. Before I do that, though, just to make sure we're all sort of happy with this. Let's suppose that someone flipped a coin 5 times. So in this case, it's a nickel. Let's suppose it's a biased nickel. Someone stuck a piece of gum on one side of it. And your coin flips came out like this, 3 heads and 2 tails. What would you estimate the bias of this coin to be?
0.6.
Right. So hopefully 3/5, right? Yeah. But why is it? Why should that be a reasonable estimate for the coin flipping test? Because it seems like the natural thing to do, right? But we like to formalize why that's the natural thing to do, right? And the idea of why that's the right answer will motivate how we fit more general probability models to data. Okay. So the standard way of fitting probability models to data is done by a procedure known as maximum likelihood estimation. Again, there are other ways that one can fit probability models to data. I don't mean to suggest that this is the only one. This one will define a particular way of thinking of quality of model fit. And once we've done that, it basically fixes this particular approach. If we had other different qualities, other different ways to assess model fit, you would end up with different algorithms, but the procedure would be very much the same. So the general idea is this. So someone gives us a parameterized family of probability distributions. So here in this Bayesian network framework, right, in this coin flipping example, right, the bias of the coin is the parameter of the model. Right? More generally for Bayesian networks, the probability distributions are the parameters of the model. Right? You need to specify them. Once you've specified them, the model is completely determined. So another simple example of this in practice that you're probably familiar with from a basic statistics course is if you wanted to fit a normal distribution to data, right, it's determined by its mean and its variance, right? So we can think of the mean and the variance as the parameters, right? They're the things that describe the probability distribution, right? More generally, we can fit any kinds of probability distributions, right? The formalism doesn't really specify how the probability distributions are parameterized. When we're fitting sort of discrete data sets, you can just basically think of the probability distributions as just some big table, right? We just need to fill the numbers in the table, right, to make sure that things sum up to 1 and define proper probability distribution. So in the maximum likelihood principle says that if you want to fit a probability model to data, then a good way to pick it would be to find the probability model that would have generated this data with highest probability. Again, we're thinking of our data as being, IID samples from some unknown distribution, just like in this coin flipping case. So the maximum likelihood principle says that we should maximize the likelihood over our parameter set. So if our probability distribution is parameterized by some set of parameters theta, which again you should just think of as being the conditional probability distributions of some Bayesian network, then we should choose those conditional probability distributions to maximize the probability of the data observations. So this makes sense, right? I have lots of different possible choices for models that I can fit, right? Because in this coin flipping task, for example, right, the bias could be any number between 0 and 1. The maximum likelihood principle says that once you give me a set of coin flips, right, a good way to pick the bias is basically to look at how likely that sequence of coin flips was under that choice of bias. Right? Simplest example, right? If we just go back to this previous slide, we wouldn't want to say that the bias of this coin was 0 or 1, right? Because that generates this sequence of data with probability 0. Right? So we pick the bias, in this, if we're following the maximum likelihood principle, we should pick the bias that generates this data with highest probability. That turns out to be 3/5. We'll work it out in a second, but that's what sort of motivates this entire model fitting process. Again, sort of attaching this, connecting this to things that other things you've probably seen before, right? So as a simple practical application, suppose you're given a bunch of exam scores and you want to find the normal distribution or Gaussian distribution that best fits this data. Right? Again, the parameters here are like the mean and the variance. Right? The maximum likelihood principle says that you should pick the mean and the variance that generates your data samples, right? The exam scores that you actually observed with highest probability. Right? That's what it means to fit this data. Right? Again, this is a simple problem that you're probably well familiar with, right? The maximum likelihood solution here is the empirical average of your exam scores, right? That's the mean, and the empirical variance is the variance of the model fit. So in many ways, this maximum likelihood principle and Bayesian networks are just a really big generalization, right, of the kinds of simple statistical model fitting things that you probably saw in an introductory stats class. Okay, so that's sort of the high-level detail. Let's actually, solve the optimization problem and convince ourselves that this is actually the right answer. It's very simple to do in this setting, and I'm going to do it here because we're going to do this. We'll apply the same kind of ideas when we figure out how it works for general Bayesian networks, and it's just easy to see here first because there's just not a lot happening in this simple problem. Okay. So someone gives us a collection of coin flips. I want to estimate the bias. The maximum likelihood principle says that I should choose the bias that generates this data with highest probability. So first, to figure that out, I need to write down what the probability of seeing this data is. So like I mentioned before, we'll typically work in log space when we solve these optimization problems. So instead of maximizing the likelihood, we'll maximize the log likelihood. It's equivalent because log is a monotonic function, but it just sort of simplifies the computation. So what I've written here is just the log likelihood of the data. So we had a bunch of independent coin flips, right? So it's the log of the probability of each one of the outcomes, right? Which turns into a sum of logs. And then the probability of the nth data sample being equal to heads, right, is just b. And the probability of it being equal to tails is 1 minus b. So if I look through, if I actually write this thing down, right, for each data sample that there was a heads, I saw that occurs with probability b, and each data sample that was a tails, that occurs with probability 1 minus b. So I just basically count up how many times I saw a head and how many times I saw a tail and multiply them by their respective probability, or log probabilities. Okay. So that's the log likelihood of the data. I'm trying to maximize this thing over b, right? I want to find the bias that maximizes this log probability. So to do that, I can just take derivatives and solve. It's a really simple calculus exercise. right? We just have to differentiate this equation with respect to b. When I do that, the derivative of the first term looks like number of heads over b minus number of tails over 1 minus b. And the optimum hopefully occurs where this thing is equal to 0. Technically, this is a constrained optimization problem because the bias of the coin has to be between 0 and 1. Right? You can't have a coin with bias 2. But we'll just check to see that there's a solution where the derivative is 0 in that space. What it tells us is that the number of heads over b should be equal to the number of tails over 1 minus b. Sort of rearranging that equation, it tells me that the ratio of b to 1 minus b should be the same as the ratio of the number of heads to the number of tails. Under the restriction that the bias has to be between 0 and 1, it tells me that there's exactly one solution to this equation. Right? That's just the number of heads divided by the number of heads plus the number of tails. So it's just, as we saw before, right, in the simple coin flipping example, right, where we had here, there were 3 heads, 5 observations. We just count up the number of heads and divide by the total number of observations. That's the solution. That's the bias that maximizes the probability of seeing these outcomes. So I'm going to pause there briefly. Questions? It only gets harder from here. Not really. It's the same thing. Just a little bit more generality. But the principle is the same. And in fact, almost all of probabilistic. So a lot of my work is sort of sits in the probabilistic modeling realm, sort of connecting probability modeling with other types of machine learning methods like deep neural networks, which again you'll get a little bit of a flavor for on the first lab today. But the principle is very much the same, right? We're looking at something simple here. It was very easy to figure out what the optimal answer was for this simple coin flipping problem. Turns out it gets much more complicated. As we fit more complicated models, it gets harder and harder. Typically they don't have a closed form solution. But the idea is the same, right? We'd like to find a setting for parameters that maximize the probability of generating the data that we saw. So connecting this again back to that spam email classification test, right? If we're trying to fit some probability model to that, we're literally assuming that the emails are being generated at random, right? From some distribution over emails that we don't know. We then fit some model to data that generates the data observations with highest probability. We can then use that thing to predict whether or not a new email is spam or not spam, right? Based on the probability that we think it's spam. All right. So to make things a bit harder, so maximum likelihood estimation, this idea, right, of just choosing the probability distribution that best fits the data in this sense of maximizing the probability of generating it, turns out to be a bit naive. So let's suppose that instead of seeing 3 heads and 2 tails, if we saw 5 heads, right? So someone flips a coin 5 times, it comes up heads 5 times. If you were following this maximum likelihood principle, right, it would say that you think that the bias of this coin is 1, right? That every time you flip it, it comes up heads. Now, I don't know. We could do this experiment here. I mean, who would be really comfortable, right, committing to 100% heads after only seeing 5 coin flips? You shouldn't be, right? Hopefully, it should make you feel a little uncomfortable, right? You don't necessarily know that you just haven't seen enough data. Maybe the bias is close to 1, right? But committing it exactly to 1, seems really severe given this sort of limited amount of data. Right. Very severe, in fact. So to handle this in practice, what's typically done is what we call full Bayesian inference. So instead of sort of just looking at the probability of the data, we combine the probability of the data observations with sort of what our prior beliefs about the world are in a Bayesian framework that looks something like this. So instead of thinking about the probability, so we can think of maximum likelihood estimation really as the probability of seeing the data, right, given a certain set of parameters. right? So in the coin flipping problem, right, someone fixes the bias, you can compute the probability, right, of seeing those observations. In a full Bayesian, statistical Bayesian framework, we think of the probability of the parameters conditioned on the data observations, right? In many ways, this is actually the optimization problem we would like to solve, right? We would like to find the setting of the parameters that are most likely conditioned on our data observations. Using Bayes' rule, if you remember back from introductory stats, the probability of the parameters conditioned on your data observations is the joint probability of the data and the parameters, which we can write as the probability of the data conditioned on the parameters times the probability of the parameters, right, divided by the probability of the data. It seems like this is a really bad idea. We don't know, if we knew some of these things, we would probably be in really great shape, right? For example, we don't know the probability of the data, right? We don't know, right? I mean, someone just gave us a bunch of stuff. We don't know how likely it is or isn't, right? We would need many, many, many observations in order to conclude something like that. In the Bayesian modeling framework, however, we can get around this because in our actual estimation task, what we really only care about is the value of theta. So technically, the denominator in this expression is sort of immaterial, right? It doesn't matter. It's the numerator that's really of interest. And the numerator is a combination of both the likelihood, which is what we were looking at before, and this probability of theta, which in this framework we're going to call a prior. The idea about the prior is that it sort of captures our knowledge about what we think should happen, right? Before we've even seen any data, right? What we think the outcome should be. It's a really reasonable thing to do in a lot of applications. For example, we collect a bunch of healthcare data, let's say, right? And we'd like to fit some probabilistic model to that data. A reasonable prior, for example, on temperature, right, that might have been collected as part of a routine health exam, would be the temperature lies in a range around 98.6, right, plus or minus maybe 10 degrees in its extreme, right? That's a good prior, right, because we know that people can't survive outside of that range, right? Now, could we conclude that from the data? Absolutely, right? If you had enough data, right, you could be really confident that the average human body temperature is around 98.6 degrees. Right? But the idea of using a prior is we take information that we might have about the data in advance, right, in order to basically bias the model into giving us better answers in sort of a limited data setting. This process, where we consider both the likelihood and some prior, is called Bayesian inference. The thing that people typically don't like about Bayesian inference is that you get to pick this prior, so it adds an additional variable to our decision-making process. It turns out that picking these priors is actually quite natural, and it happens all the time in a lot of machine learning applications. Again, we don't really have time today to go through all of sort of the minute details. But it turns out that in a typical machine learning application, picking a prior often corresponds to picking a regularizer. So if you ever fit other machine learning models to the data and you added some L2 penalty, so you're training your neural network and it has some L2 penalty, that L2 penalty is actually a prior over the parameters in a Bayesian statistical sense. We can make that really precise. I don't have time to, but that's really the way you can think of this prior. It's biasing your solution.
So does the math work in a way that the more and more data you have, the less relevant the prior gets?
That's correct. So taking a look at this expression, right, the probability of the data conditioned on the parameters, right, this is a big product of things, right? It's because we're assuming our data is independent draws. So if you have 1 million data observations, this thing is a product of 1 million probabilities, right? And as you said before, right, as you multiply a bunch of these things, tiny numbers together, right, what's really going to end up dominating this expression is the likelihood, not the prior. So actually, in the limit of an infinite amount of data, this Bayesian inference approach and the maximum likelihood approach are identical. Right? They give the same answer. They only differ when you have a finite amount of data, right, where the prior might bias you towards something else.
Good.
Yes, good, right. So, yeah, what we don't want to do is, and a lot of my students often get confused with this. The one that we don't want to do is bias the model to giving us incorrect answers, right? We don't want to do that, right? The idea is that the prior just sort of helps us correct in sort of limited data settings in order to prevent what we would typically call overfitting of models. Other questions? So the process of finding theta via this approach, right, where we basically maximize the numerator of this expression, so the likelihood times this prior term, is called map inference. It stands for maximum a posteriori inference. The reason what that comes from is that this probability of theta conditioned on the data is called a posterior probability. It's the probability of the model parameters conditioned on the data observations. All right. So let's see how this sort of works in practice with with our simple coin flipping example, and then we'll sort of work out the details of maximum likelihood estimation or map estimation sort of more generally for Bayesian networks. So here we go. Again, we're in this setting where someone's flipped a coin a bunch of times. Let's say here we're given our coin flips. We again have 5 of them. Let's say the coin this time comes up heads, 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 tails. And we'd like to use map inference, right? So this Bayesian estimation procedure in order to estimate the bias. So to do that, right, we need to pick a prior probability distribution for the bias. Okay? Like I said, this is the seemingly hard part of this process. How should we pick a prior distribution for the bias?
Depends on how much trust you're putting in the bias.
Sure, that's true. What might be just a reasonable prior for the bias? Assuming you do think coins don't always land heads.
It's mostly 1/2 that gets cut off at 0 and 1.
So between 0 and 1.
Yeah. Well, so we could pick a prior that just says uniform distribution over all values between 0 and 1. That's a perfectly reasonable prior. That is a very boring prior. In fact, it's easy to check that prior reduces to maximum likelihood estimation. In fact, maximum likelihood estimation is, if we just sort of look at the formula again here for a second, if your prior probability of the model parameters is independent of the model parameters, right? So for example, if our probability of the bias is the same for every value between 0 and 1, then basically this term, we can ignore it, right, in the optimization, right, and it just gives us the likelihood. So although that's a completely reasonable choice, it doesn't encode any information about the problem, right? So maximum likelihood estimation is really saying, I think everything's equal, right? And we'd like to introduce a prior to make things a bit unequal.
Let's make that 10.
Yeah, so okay, so that's totally reasonable, right? The video person's probably gonna dislike this. You're not gonna see it very well, but sure, you could pick, probability distribution. I don't know, we'd have to pick things so that they, normalize to 1, but you could have something like this. Right? It'd be perfectly fine. That's, assuming that this thing integrates to 1, it defines a probability distribution, right? And we could use this thing as a prior. You can pick lots of priors. Lots of things are reasonable. The thing I usually get from students in my class is everybody wants to pick a normal distribution. Right? So they might say, oh, why don't we use a normal distribution centered at 1/2, right, with some fixed variance. You could do that, but sort of draw that pictorially. Right? That thing has a problem in that it assigns non-zero probability to things outside of the range 0, 1. And we don't really want that because, again, that's that's encoding, that's really dumb because you know, for example, that this just can never happen, right? So you really shouldn't put any probability there. Another caveat about prior probability distributions is you need to be a little bit careful. You can't just pick anything. So we have this discussion saying like, oh, well, if you have enough data, this first term sort of swamps the second one. That's true, except in one situation where you pick a prior probability distribution that puts probability 0 on something. If you do that, then, for example, let's say in the coin flipping task, I pick a prior probability distribution that puts probability 0 on any bias less than 1/2. I can do that. That's a reasonable thing, and it's uniform elsewhere. I can do that, but if the best fit theta, right, actually was less than 1/2, right, this particular model would assign probability 0 to that outcome, and that would bias this model, even in the limit of infinite data. Right? You can't overcome the fact that you think things have probability 0. So there is some nuance here, But in practice, it's usually quite easy to pick these things in some reasonable way. Let me give you, I'll give you an example of like how it's done for the coin flipping one in a second, but just sort of at a higher level example of applications. Right? Let's suppose that we were trying to estimate performance of, say, like sports teams, right, or individual players on a baseball team, right? I've got some observations about how they're performing this year. I've got sort of historical observations of how they performed in past years. A reasonable prior might be, in the absence of seeing how they're performed this year, right, might be to look just how did they perform last year, right? That's my prior belief in how they performed this year, right? Maybe I tweak that a little bit based on age and whatever, right? But I can use sort of knowledge I have about player performance, right? That sort of doesn't require me seeing this year's data, right, in order to put down reasonable predictions, right? And this is often how these things work, right? I mean, you see like, oh, before the football season even starts, some team is like really highly rated. Well, how could that be, right? They haven't played any games. Well, this is our prior belief. It's a holdover from last year's data observation, right? So our prior is somehow encoding that, right? That we would be really surprised, right, if the team that won the Super Bowl last year like is going to come in last in the rankings, right? Okay. So let me give you an example of a prior that's typically used for this data estimation task. So the typical prior that one picks here is a beta distribution. So I'm bringing this up because we're going to talk about the generalization of the beta distribution, the Dirichlet distribution, in sort of the application that I have in mind this afternoon. But the beta distribution basically does the following thing. It's a probability distribution over the bias that's parameterized by two different numbers, alpha and beta, where alpha basically is a parameter affecting the like positive outcomes, so like in this case the heads of the coin, and beta affects the tails of the coin. And this thing is normalized, so it has to integrate to 1, so there's some normalization constant here. This little symbol means proportional to. I don't want to compute that constant. In fact, it doesn't even have a closed form.
Good question.
Yep.
Is the beta distribution typically chosen because it makes math easier to analyze?
Yes, it does. Right. That's why we'll choose it here. I want to emphasize something, though. So sometimes if you would go, so there's a bunch of different camps when you talk about people that do statistical, fit statistical models to data. One camp of those people is the classic statistician, right? And the classic statistician would actually pick the beta distribution because it makes all the math work out beautifully, and basically everything has a closed form. I'm from the other camp. I actually don't care whether or not that turns out to be the case. I'm willing to exert computational power to solve the problem. So I don't care whether or not it has a closed form. For our purposes here, for illustrative purposes, it's nice that the math works out in closed form. But there's no reason to pick that, right? We could pick this funky distribution. The math will not be beautiful at all. It'll be really ugly. It won't have a closed form. But it's still a reasonable prior, and we could solve the problem in this setting. It just requires more computational effort, right? Rather than just sort of simple derivative.
So how much does generally how much does your outcome change depending on what prior you pick?
Well, so it depends on a lot of things, right? One, it depends on how much data you have, right? If you have an absurd amount of data, the prior is meaningless, right? Because its bias is meaningless, unless you also have sort of an equivalently large number of parameters to fit. So this is a good caveat for if you taking a look at like sort of fitting like deep neural networks to data, right? Those are very large parameter models. You typically have a lot of data, but the amount of data is sort of commensurate with the number of parameters needed to fit the model, right? So the prior is sort of really helpful when you have limited data, small number of parameters. Then it'll sort of help drive you in the right direction, right? So how useful or not it is, right, really depends on the actual data and how good your prior is. So you can often see this, right? Like, again, using the sort of sports analogies, right? Sort of predictions for next season, adjust very quickly after the first few games are played, right? Because we have some preconceived bias, but as soon as we start seeing, like, I don't know, half the team is injured, right, in the beginning of the season, right, it really changes our notions, right? So very quickly, we should adapt, right? Even though our prior was, was pretty good in that case, right? We'll very quickly, change our minds if we see really poor performance for a particular team. I should really stress, though, that like I said, you should really think of priors almost as regularizers, right? They're sort of biasing simpler models under some notion of simple. And basically, almost all machine learning methods have some kind of prior or regularizer that's sort of really important to make the model fitting, accurate in practice. This is just sort of the statistical version of that thing. So what does the beta distribution look like? So it actually has the nice property that its support is just between 0 and 1, so it only places non-zero probability on outcomes between 0 and 1. And as you choose different values of alpha and beta, you get sort of funkier distributions over the interval 0, 1. They're basically all unimodal in some sense, although you can get sort of weird things that have sort of peaks at the boundaries. But a reasonable prior, for example, right, if we really thought our coins were close to bias 1/2, might be this purple line, which is the choice of alpha and beta being equal to 2. It sort of encodes the notion that we think that sort of most coins are unbiased, right, unless we see sort of significant information to the contrary. But of course, I don't know if you had some reason to believe that the coin was biased to tails or biased to heads, right? You would pick the alphas and betas accordingly. Now, as was pointed out, right, I'm going to work out the map estimation for the coin flipping problem with this bias, with the prior being the beta distribution, just because the math is easy. But you could pick any prior that you want. I think I already said these things. All right. Oh. So coming back to the coin flipping example, so if I would use this beta prior, I would take my likelihood. I would take the likelihood of the data and I would multiply it by the probability distribution of this form. Right? If we think about what effect that has on the coin flipping problem, well, the likelihood looks like b to the number of heads, right, times 1 minus b to the number of tails. That's the probability of seeing, that many heads and that many tails in a sequence. If I multiply by this, it has the effect of basically adding a fake number of heads and a fake number of tails, right? How many fake heads and tails I add depend on the choices of alpha and beta, right? So, if alpha is 10 and beta is 10, it's like adding 9 fake heads and 9 fake tails, and then doing the maximum likelihood estimation procedure, right, based on that. So it makes sense, right? So going back to the picture of the beta distribution, it makes sense, right? That this purple thing, right? It's the symmetric one where alpha and beta equal 2, right? I basically added 1 fake head and 1 fake tail, right? And it makes the boundary solutions of all zeros and all ones basically occur with probability 0, right? Or very close to 0, right? I think they're very unlikely, right? Unless I see enough data to contradict that. Okay. Questions about map estimation, maximum likelihood estimation? So we're going to do it for Bayesian networks here in a second. Again, the reason for doing this, I promise you, the application is really cool. It's just we really have to have a good framework for probabilistic model fitting. And we're talking about just very simple models here, I admit. We'll see a very complicated model in the afternoon that hopefully you'll really like and has a lot of applications. But it just takes a little bit of background for us to really believe that it's a reasonable thing to do. OK. So if there's no questions, let's take a look at how this maximum likelihood estimation procedure works out for Bayesian networks. So like we said, the coin flipping problem is really, it's a simple example of a Bayesian network, right, where there's just sort of one random variable that just an indicator random variable, right, heads, tails. Right? So we want to generalize that to make this as generic as possible. Let's consider the maximum likelihood estimation for Bayesian networks where someone has given us the directed acyclic graph. So again, I don't want to, we're not talking about what's the right structure to fit to data. That's sort of a separate problem for now. Let's assume the structure is given, and someone gives you a bunch of data samples. I just want to figure out how should I choose the conditional probability distributions for my Bayesian network to maximize the probability of seeing the data. So again, we can maximize the log likelihood. In this setting, it looks like, what does the log likelihood look like? Well, it's a sum over all the data samples of the log probability of that data sample. In the Bayesian network case, right, the probabilities, the log probability is given by, the probability is given by this product of conditional probability distributions. So the log probability is a sum over all the conditional probability distributions in the model. And those conditional probability distributions, remember, again, are the probability of the ith variable conditioned on its parents. So I'm gonna write it like this to emphasize this is sort of a parameter of the model that we're optimizing over. But this theta xim, x parents im, should be taken to be the probability of the mth data, probability I in the mth data sample conditioned on its parents in the mth, their values given by the mth data sample. That's the log probability of the data under this Bayesian network model. So again, it looks very similar to what we saw before, right? So some of these things will be the same, right? So if you look at all your data samples, right, some of them will have, xim equal to 10. All of the ones that have xi set to 10 and have the same value for the parents, right, there's just one parameter for that thing. Just like in the coin flipping problem, right, there's one parameter for heads, and the parameter for tails is 1 minus the parameter for heads. Right? Same thing here. Right? These are actual probability distributions. They sum to 1. So we can apply exactly the same strategy. Right? We can take derivatives of this thing, set it equal to 0, and solve basically to figure out how we should pick the values of the conditional probability distributions to maximize the log likelihood. Now, as a sanity check, to make sure not everyone is completely falling asleep. By analogy, what do you think the log likelihood should be for these models? Right? So we saw for the coin flipping problem, right, the maximum likelihood estimator was just we counted up the number of times we saw heads and divided by the total number of data observations. Right? That gave me the probability of heads in the model. So if we have a Bayesian network model, right, where we have a conditional probability, let's say, probability, it's like this, we've got y, say, x1, right? If we want to figure out how should we pick the probability of x1 conditioned on y, how do you think we should pick it? So technically, this model makes the assumption like this, right? This one we saw before in some sense, right? If I want to figure out what's the probability of y, I really think of y as like a coin flipping process, right? So I would just count up the number of times I saw y, right? And that, in a particular value, divide by the total number of data samples. And that seems like that should be the right answer here, right? The question is, what's the right answer here, right? Intuitively, before we just work out the details.
Are we assuming x1 is independent, or?
Nope, no assumption here. It could be anything. So maybe a better way to say this is that in the maximum likelihood estimation task for the single coin flipping problem, right, we saw that the maximum likelihood estimator was just the empirical probability distribution, right, of the outcomes. This thing here is a conditional probability distribution, but it also has an empirical analog. There's sort of an empirical probability distribution of x conditioned on y. Right? It turns out this will be the right answer here as well. And intuition should tell you it's basically this for the same reason, right? We're going to end up just counting up the number of times we saw things in certain configurations and dividing by the total number of configurations. Let's work it out, though. It's not very hard. It basically boils down to the same argument as before. So the log likelihood sums over all the data samples and the sum over all the conditional probability distributions of each variable conditioned on its parents. We can swap the order of summation here because these are finite sums. So it doesn't matter which order we sum them in. So if we think about summing over the inside, over the number of data samples first, for each fixed value of the, for each random variable in our model, then we can rewrite this in basically the same way that we did before. In the coin flipping case, right, we just looked at how many times did we see heads and how many times did we see tails. The generalization here is we look at all the different combinations of xi and its parents we could possibly have. So we sum over all the different possible values we could have. We look at the number, we multiply by the number of times we saw each one of those combinations in the data set times the log of whatever the probability was that we got that. So these two things are equivalent. It's just a rewriting, right? Here, this is summing over all the data samples. Here, we're summing over all the possible values, right? Multiplying by how many times we saw those values actually in the data. And now it's basically in the exact same format as it was before, so we can take derivatives and solve. It's worth pointing out that our job was slightly easier in the coin flipping case because we wrote the bias for heads and the bias for tails as 1 minus the bias for heads. So there was basically only one parameter. Here we have a bunch of parameters, and each one of these things has to be a conditional probability distribution, meaning that if I took data and I summed over all different values of xi, it should sum to 1. It's supposed to be a conditional probability distribution. So still, taking derivatives and solving, we find exactly the same result as before, basically because it's in the same format, that the optimal choice for the setting of this conditional probability distribution is just its empirical setting from the data. Another way to write that is that the maximum likelihood estimator for the conditional probability of xi conditioned on its parents, right, for a fixed value of xi and a fixed value of its parents, we just look how many times we saw that particular configuration. Right, we saw xi and x parents of I together in the data set and divide by the number of different times we saw that value for x parents of I. It's just an application of Bayes' rule, but it's in the empirical setting because it's based only on the counts in the data and nothing else. We call this thing the empirical conditional probability distribution of xi conditioned on its parents. All of this works out in basically the same way as the coin flipping problem, and that's basically just because of this assumption that we made for the Bayesian networks that it can be written as a product of conditional probability distributions of each variable conditioned on its parent. So fitting Bayesian networks to data is very easy. We just count up the number of different times we see certain values in the data set, divide by the total number of values, right, to fit these things. So it's very straightforward. Like I said, that's why we're focusing on this particular type of probabilistic model because it's easy to do. It's easy to fit them in practice. The bigger trick turns out to be optimizing the resulting distribution, right? Actually doing the prediction thing, solving the prediction task. But we don't really have time to sort of get into the nuanced details of that today. Questions like about any of this stuff, Good. Well, you'll get a little bit of chance, like I said, to play around with them, a bit in the first lab. We've done sort of the hard work for you of writing the code that does all the prediction. Basically, what you need to do is just fit them to data in an appropriate way by calling the appropriate functions and building the appropriate models, which we'll walk you through a bit in the lab. Hopefully, at the end of the lab, you'll be convinced that this sort of really simple approach actually can be quite powerful in a variety of different settings. So in the lab, you'll get to see this applied to an activity recognition task in video. So again, we did the hard part. We fit some million parameter neural network to data. Here, the data are videos of people cooking in a kitchen. And the goal is to predict what's happening basically in each frame of the video. The neural network by itself it can be reasonably accurate, but when you combine it with sort of simple probability models, you can sort of smooth out the behavior, right? So we can take advantage of the fact that we know things are continuous over time. So you get to play around with that a little bit in the lab. Okay. Coming back to the motivating problem from the beginning, again, is the spam email classification task. So now that we understand how maximum likelihood estimation works, Again, we take our spam email, we featureize it, right? We collect it into a big feature vector. Let's suppose there's only 6 words, or oops, that should be a 5. There's only 5 words in our dictionary, so our naive Bayesian model looks like this for the problem, right? Y here we think of as the label for the spam email. So we take all of our spam emails, we convert them into this 5-dimensional vector plus the label. The maximum likelihood principle says that if we want to fit this thing to data, right, we just count up how many times we saw the spam or not spam. That gives us the probability distribution for y. For each one of the words in the dictionary, we look how many times we saw it for each label, right? So we look how many times we saw word 1 when the label was spam, how many times we saw word 2 when the label was not spam, right? That gives us this conditional probability distribution, right? So we just scan through the data, right, to figure these things out. Why might this be a reasonable thing to do? And like I said, this with like an appropriately chosen feature vector, which is basically what I have here, with a few additional tweaks to it, basically yields 98% accuracy for this prediction task. The reason is that I get just this morning I woke up to 6 spam emails about random made-up conferences in faraway places. It's sort of very easy to recognize them, right? A lot of them have like the same kinds of classic keywords. Like, I never get a legitimate email about anything in Nigeria, right? So if Nigeria is in the email, then I should think that thing is spam with probability 1, right? Other sort of simple features we could encode, right? Like sequences of number of capital, sequential capital letters, amount of contiguous punctuation. No one ever sends me an email with 10 exclamation points in a sentence, right? Or more punctuation than actual text. These kinds of things. They're very simple feature heuristics, but they turn out to be like incredibly powerful for this particular task. It just turns out that it's just that simple. We can't hope that such simple models will really work for much more complicated machine learning tasks. Right? We'll need more complicated models that express the right kinds of relationships between the features and sort of the labels we're interested in predicting. But the principle is really very much the same. As actually, as an interesting side note on this stuff, oftentimes I'll have colleagues that will come to me, in more applied areas, like people in software engineering, and they'll say, "Oh, I've got this machine learning task for you," and they'll describe it to me, and they're like, "Oh, we're going to apply, we want to apply, deep neural networks to solve this problem." And I always say, "You tried the dumbest stuff you could think of first." I mean, this is a great example of that, right? I mean, why would I apply a deep neural network for this problem, right? It actually will probably perform much worse than this simple, dumb probability model. This thing is very simple. It's not making a lot of assumptions about the data that are really particularly unreasonable in this spam email setting. Right? If I go to fit a neural network to this, it's much more complicated. I might need a lot more data, right, to actually get good predictions. So start with the dumb stuff, and sort of build up from there. Right? Even when we talk about fitting probability models, we'll often start with fitting really dumb probability models, see what the performance looks like before we start fitting more complicated things. Because simplicity really is key here and in many machine learning applications. You won't really want the simplest model that describes the data, not just the best fitting model. Right? We can find lots of best fitting models that just basically memorize the data. Right? We'd like something to abstract to a bit of a higher level. Okay. So like I said, you'll get a chance to play with these things a bit in the lab. So the kinds of models that you'll see in the lab look a lot more like this. So there's a particular application of Bayesian networks that perhaps the one that really brought them to prominence in some sense are what are called dynamic Bayesian networks. In these settings, you basically have a collection of random variables that occur in sequence over time. Right? So you should think of maybe x and z in this setting as observations of some time series process at different time slices. And the y's might be sort of some outside information that you have from some sensor that informs this process. And it's a much, although the structure of the model is very straightforward, it's a much more complicated model because it involves, a lot of sort of local connections between individual variables. And it turns out that solving prediction problems in this model is much more complicated than it was in our naive Bayes setting. And just to emphasize that a little bit, remember that if you want to do prediction in this naive Bayes model, you just try both values of y in this probability distribution, whichever one is larger, that's the prediction, right? When we talk about models like this, right? Say I want to predict, the last 3 time series, steps in the sequence from the first ones. It's not as easy as just plugging in all the values, right? There might be a lot of values I have to plug in, perhaps exponentially many of them. So I have to be careful when we start talking about more complicated models. And it turns out that almost all of the work in probabilistic modeling is really focused on that later task. That's what we call like the inference task. Because it turns out that if you can do the inference task very well, you can basically do all the other tasks very well as well. Okay. Well, good. I am surprisingly ahead of schedule today, which is good. I was actually worried I would be a bit behind schedule. So in summary, what I've really shown you here is just a really simple way to fit a simple type of probabilistic model to data. Right? This probabilistic model allows us the flexibility to model a variety of different probability distributions, and to sort of simply fit them to data just by doing computing empirical counts. We saw the generalization of that, which was map estimation, where we can introduce a prior. The idea of introducing this prior, right, is to prevent what we call overfitting, right, where the model basically commits too much to one extreme without seeing enough data, right? We saw that in the coin flipping example, right? If we only flip 5 coins, we shouldn't commit to probability 1 or 0. That's probably really unrealistic. We can use, we didn't write it down, but we can use the same strategy, right? For general Bayesian network fitting, right? Again, using beta distributions or their generalizations to sort of add fake samples into the data in order to bias ourselves in the low data limit. What we're going to talk about in the afternoon is topic modeling with Bayesian networks, which turns out to be a lot harder to do than just simple fitting probability models to data. It introduces some additional complications, and it will also not be a supervised learning problem. So in the topic modeling application, we won't be given the correct answers. Instead, someone's just going to hand us a big blob of data and say, tell me something interesting about it, which is sort of a very distinct task from this supervised learning task where someone has already told you what the answer should be. We just want to find a model that best fits the answers that we've seen. Okay. Well, great. I think there's supposed to be coffee now. So